Nice.
Okay. Okay,
Awesome.
I got it. Let me maximize.
Uh-huh.
Okay, so now I know how to do that. AI Engineering Chapter 3, Evaluate Methodology. So I had a lot of fun studying this chapter. And Chapter 1 covers different evaluation methods used to evaluate open ended models. So, like language models, where it's not always as simple to make to evaluate it. It is more challenging because it's not always simple yes and no. You have like infinite number of answers. So we'll go across. We'll review some of the fun ways to evaluate open-ended models. Chapter 4 is focusing more on specific methods to select models. I haven't read chapter 4 yet, but so I guess chapter 3 is a little bit more theoretical. Um, so let's go to the next slide. So here we have, uh, what is the motivation for evaluating foundational models? So as noted, foundational models are very open-ended, just like natural language models, and so AI is used. There's an opportunity for catastrophic failure. What happens if you got some AI intelligent software running uh, your business and it does something horrible and you lose all your customers. So we have to be able to evaluate models so that we can prevent, going bankrupt. I mean, so it's very important. Uh, so evaluation is key, but it's very difficult with uh, with certain machine learning models that are more open ended. It's more challenging to evaluate. So. Uh, Otherwise, the risk would outweigh the benefits if we can't make it safe and reliable. And there is a challenge there because it is more difficult to have an open-ended model. There's more challenges with the evaluation process. So let's go on, and we're up to the third slide. So since many foundational models, are you guys still there?
Yes, we're here.
Oh, okay, great. So many foundational models have a language model component. And so this chapter will provide a quick overview of the metrics used to evaluate language models, including entropy and perplexity, which I found very, very interesting. So again, I didn't introduce myself. My name is Patrick, by the way, and I did 20 years overseas with the State Department, and basically my background is strong network administration. And on my own, I've always been studying everything. So I studied Python coding, Rust, whatever, and of course, making websites and Apache web server and other ways to do things. And of course, over time, I started getting more into machine learning and AI because I could tell it was going to become very important. And also, you can't always solve, if you can make a machine help you solve puzzles, it can be a great way instead of you trying to manually, hard code everything. It doesn't always work out that way. So that's why I started getting into machine learning, but I'm still like a baby. I have a lot more to learn, and so I got into logic after college. I only took one course in logic. I started studying logic, set theory. Now I'm studying topology, all sorts of math on my own, and I love it. So
Nice.
so and now you can use AI, and it's like your math teacher. So this is exactly what I do all the time. Oh, okay. Anyway, back to the course. These metrics are essential for guiding the training and fine-tuning of language models. So things like perplexity and entropy. And this book focuses on automatic evaluation, which includes both exact and subjective evaluation. Okay, so the fourth slide, challenges of evaluating foundational models. So like we were talking, we could have a catastrophe and lose all our business. The more intelligent AI models become, the harder it is to evaluate them. Because, for example, if you have a PhD thesis, sometimes it's so subtle you might not know the difference between someone that's faking it and someone that really is the authority and knows the dicey, subtle niceties of every little point. So it's harder to evaluate something that's very sophisticated and sometimes know whether it is the real thing or not. And also, evaluation becomes very time consuming on sophisticated tasks. And there is this open ended nature for foundational models. And undermines the traditional approach of evaluation. Okay, because the traditional approach is sort of more of simplistic ground rules for truth, but with the open nature of foundational models, it's like anything between, for example, 1 and -1 or 0 to 1, and you got an infinite number of real numbers between that, and all those possibilities of defining certain things. It's so infinite that it's hard to define like true or false or 5 points only. Instead, you could do that, but then you got to do that a million times. It doesn't become feasible. That's the problem with open-ended nature of foundational models. And so we'll have more challenges also evaluating it because we don't have a simple model with simple just a few ground rules. It's much more sophisticated. The open-ended models, for a given input, there are so many possible correct answers. Yeah, exactly. So the fifth slide, let's see, the challenges of evaluating foundational models. It's impossible to curate a comprehensive list of correct outputs to compare against. So okay, I kind of already hit that. And since foundational models are frequently treated as black boxes with details of its model architecture and training data hidden, we are forced to evaluate such models on its outputs. Benchmarks become saturated once a model achieves a perfect score also. And this is a problem because once you hit a perfect score, it's not as effective in terms of being competitive with future developments and all, because it's sort of saturated at that point. And so you always in defining and clarifying whether it's competitive with newer models, and so it's saturated at that point. So now we're up to the sixth slide, and the challenges of evaluating foundational models. Well, that's the area. So Chip Huyen, the author of the book, noted an exponential curve in the GitHub repositories focused on evaluation tasks. However, even though there's increased interest, all the other areas of the AI pipeline are much more popular, so there's a problem there. So the bad news is that despite the increased interest in evaluation, it lags behind in terms of the interest in the rest of the AI pipeline. Inadequate investment leads to inadequate infrastructure, making it hard for people to carry out systematic evaluations. And instead, many AI practitioners eyeball results or have a limited set of prompts to evaluate models. And this is a problem because this is not systematic evaluation. Okay, so now we're on slide 8. We have foundational models evolved out of language models. And for these models, the performance of the language model component tends to be well correlated to the foundation model's performance on downstream applications. So, in other words, if we can test the foundational model and evaluate it and know how well it performs, we'll have a good idea how well applications that are hosted or integrated into that environment, how well they will perform as well. So it's very important. We'll have a better idea of how to evaluate not only the foundational model, but we'll have a good sense of how well applications built on it could perform as well. Therefore, a rough understanding of language metrics can be quite helpful in understanding downstream performance. So again, I'm new to ML to a certain degree. I've been studying it on and off for 5 to 10 years, at least 5 to 8 years. And so I'm not an expert on everything, but what's fun is nowadays you can use AI to help you learn AI. So one of the big giants of the of artificial intelligence or that kind of stuff, that his ideas and theories are very seminal, is Claude Shannon. He published a 1951 paper entitled Prediction and Entropy of Printed English. So it was very groundbreaking, and still to a large extent, these concepts are used in machine learning and AI. So four metrics were kind of derived from Claude Shannon's work, including entropy, cross entropy, perplexity, and bits per character and bits per byte. So all four metrics are closely related. If you can derive the value of one, you can compute the other three accordingly. And so now looking at slide 10. And so we have the four metrics referred to as language model metrics in this book can be used for any model that generates sequences of tokens, including non-text tokens. And that latter part refers to like multimodal AI models, like image data set, audio data set. So multimodal, it's not all text. So sometimes we have different models out there to represent a database that is all about how to, you got a system to help you draw stuff. So you articulate, draw a beautiful sunset and a volcano with the ocean in the background, blah, blah, blah. And so then it somehow draws from that data set primitives to help it draw, make an image, it's really incredible stuff. And so we can use these metrics not only for text data, but also for data sets that are all about image data or audio data, video data, the different multimodal stuff out there that's being developed. And that's really exciting stuff. Recall that the language model encodes statistical information. And the more statistical information that a model can compare, the better it is at predicting the next token. And in ML lingo, a language model learns the distribution of its training data. The four metrics help evaluate how well such models learn. So on to the next slide. So we will talk about the first most basic metric, and that would be entropy. Entropy measures, basically entropy measures like the state of disorder in a system. So looking at flipping the coin, saying it a different way, it's all about how much information remains. So the higher the entropy, the more information the token carries. Well, I think actually the higher the entropy, the more it would degrade some of that information. The less entropy, the more information would remain. But at any rate, these are just niceties, and you have to look at the equation, and we'll look at that in a bit. And it's actually a lot of fun. And like I said, I'm not expert about everything, but I'm beginning to get a lot more knowledgeable and in what it really means. And so it's exciting when you can get into the details. As discussed in chapter 1, a token can be a character, a word, or a part of a word. And Claude Shannon, and Claude Shannon's theory, he originally did it more on a character. So, his ideas were extended and complementary ideas. So now a token can be more than just a character. It could actually be a word or a part of a word. Tokenization, which we had already discussed in chapter 1. So Shannon said the entropy is a statistical parameter which measures, in a certain sense, how much information is produced on the average for each letter or word of the text in the language. So entropy can be the state of disorder or chaos, or how much information was degraded, and the flip side is how much of that information remains, is the way I interpret it. And like I said, it's better just to look at the mathematical equation to get a little bit more of the intuition of what's going on. So the next slide 12, Claude Shannon continues, if the language is translated into binary 0 or 1 in the most efficient way, the entropy is the average number of binary bits per letter of the original language. So we'll see a diagram that kind of shows what that means. So Chip Huyen continues, let's use a simple example to illustrate this. Imagine you want to create a language to describe positions within a square, as shown in figure 3-4. And so here is the figure that's cited, figure 3-4. And so you could carry 2 bits, or you could have 4 bits. That a language of two. Okay, so we have 2 languages that describe positions within a square. Compared to the language on the left, A, the tokens on the right, B, carry more information but need to have more bits to represent it. And likewise, you can have some entropy that degrades some of it. So here, we're up to slide 14. If your language has 4 tokens shown in B, figure 3-4, each token can give you more specific positions, upper left, upper right, lower left, lower right. However, since there are now 4 tokens, you need 2 bits to represent them. The entropy of the language is 2. So you can express, you got 4 bits, you can express like 2 characters, and you got an entropy of 2, I guess, something like that. So you got 4 tokens, and you need 2 bits to represent them. Okay, I see. You got 4 bits, you need 2 tokens to represent them, and the entropy is 2. This language has a higher entropy than the one with only 2 bits, since each token carries more information, but each token requires more bits to be represented. Okay. Intuitively, entropy measures how difficult it is to predict what comes next in the language. The lower a language entropy, the more predictable that language. Okay, that's interesting. So the lower the entropy, the more predictable the language, but then I guess you can't do as much with it. Anyway, I don't have complete mastery of every intuitive detail, but I get the general idea, and we're about to get into the math of it, so that will be a lot of fun. Slide 15, cross entropy. And again, when we were talking about entropy, we're just using one set P, but now with cross entropy, you're comparing 2 sets, P and Q, and we'll get into that. So a language model's cross entropy on a data set measures how difficult it is for the language model to predict what comes next in the data set. So it's like entropy is sort of like the way it is in terms of the actual data, and then cross entropy is like a comparison against a prediction or something, and then it knows the difference of what is and what could be, and it says, okay, there's a loss, and therefore it should be like that. A model's cross entropy on training data depends on 2 qualities: the training data's predictability measured by the training data's entropy. Okay. And how the distribution captured by the language model diverges from the true distribution of the training model. I have some better quotes. I could easily rewrite this already, but you get the general idea, and it's coming right from the book. Okay, so now cross entropy continued. So entropy and cross entropy share the same mathematical notation, H. Now, H is entropy as I understand it, but it all goes down to entropy, and then it's how many sets you're using. So with entropy, you basically are using P. Let P be a true distribution of the training data, and Q be a distribution learned by the language model. Accordingly, the following is true. The training data's entropy is therefore H, and P as a parameter. So H is a function of the entropy, and P is the set of possibility distribution values. And so another way of calculating, for example, is the divergence of Q with respect to P. It's similar to cross entropy. It can be measured using the Kullback-Leibler divergence, which is mathematically represented by DL. I forget the. Anyway, we'll get into that in a moment. But I have it right over here. It's quite interesting. Right here, KL, the Kullback-Leibler, is a contrast that measures the difference between a probability distribution, between 2 probability distributions, P and Q. Namely, KL divergence quantifies the amount of information loss when Q is used to approximate P. So it's all about finding that, but cross entropy and also the KL is ways of measuring 2 sets and how they are, how they diverge, and therefore that helps you make predictions or get closer to the way things should be. Anyway, here we have The model's cross entropy with respect to the training data is therefore HPPQ, which would be equivalent to HP plus, looks like the divergence of PQ. Now, when it's like that, P double bar Q, I'm a little bit weak on that notation specifically. That almost looks like probability theory, where given P, there the hypothesis P and then Q or something. Anyway, I'm not exactly sure how that works mathematically, but I could easily research it more. So the cross entropy isn't symmetric, and so anyway, that's just a mathematical property, and a language model is trained to minimize the cross entropy with respect to the training data. So it's it's all about that gradient descent. You can think of a model's cross entropy as its approximation of the entropy of its training data. All right. So now we are up to slide 18. However, that last statement is perhaps somewhat overgeneralized. It's probably better to think of cross entropy as potential information loss. Anyways, I had, after studying up more, I reached the conclusion that cross entropy and also that KL divergence, they're kind of more about making a prediction between like the probability and versus the way the probability distribution is versus something that's predicted, and it helps that gradient descent. It helps you predict and get a better, stronger model where the answers are more accurate. So it also talks about bits per character and bytes per character. This is very interesting. Specifically noted here is that right here, in fact, is that sometimes the bits per character is like not going to work too well with UTF-8 that are multi-byte, where it's between 8 bits up to 32 bits. So for that, you'll probably need the bytes per character. It'll be more robust and handled properly. So iterate. There are different ways these things. We got 4 different major metrics, and so I think we'd probably be doing bytes per character if we needed one of these two. So perplexity is the exponential of entropy and cross entropy, and it is shortened to PPL, or sometimes PP, I think, given a data set with a true distribution P. Its perplexity is defined as, so you got the PPL function, and it takes the set of the probability distribution, and that is equivalent to taking 2 to the P HP. So that would be like entropy, and you put into it the probability distribution, and you're saying that 1 or 0, or a 2-bit language, for example, could be raised to the power of HP, and so potentially that would be a very large number. That would give you like I don't know. I'd have to study it a little bit more to get. Last week I was already on it. I'm already forgetting. So anyway, with the second one, PPL P comma Q, there we're comparing 2 sets, and so with the first one we got a type of perplexity with with only P. And here you got a perplexity with using two sets. That's very interesting. If the cross entropy measures how difficult it is for a language to predict the next token, perplexity measures the amount of uncertainty it has when predicting the next token. Oh, okay. That makes sense. Sometimes ML frameworks use NAT, natural log, which is a unit of entropy and cross entropy. Well, I mean, it is, in other words, instead of being 2 binary, you can do decimal 10, or it's often ML frameworks prefer to use NAT, which is symbolized by a fancy E named after the famous mathematician Euler, a Swiss mathematician. And so by using that base, somehow that constant, I forget the exact number, but that constant is friendly with logarithmic information, I think. So it somehow plays well, and it makes it very useful. Like as an analogy, stock market data, you can have linear for usually present day stock market activity, and then you can have a logarithmic representation of the stock market data, and that's better. It smooths it out so that if you're looking at 3 months or 2 years of stock market data, it tends to make it look better. So you can look at stock data linearly, using a linear kind of equation, or you can use a logarithmic kind of way of looking at it. It's the same thing here. So you can use different bases, binary versus decimal versus Euler, the NAT, and it's the same data. It just gives you different ways of looking at it, and can be useful. Because, for example, with stock market data, the linear is more sharp and jagged, and is very good for right now. I want to know where things are going. But as you look at 2 years of data, it's easier to use a logarithmic kind of thing. It's more useful. So here we're going to get into finally the equations, and this is actually really fun, and the intuitions become more readily available. Entropy measures the average uncertainty in the probability distribution P for a discrete random variable, actually set, if you will, X, with possible outcomes X, a little subscript I, and the probabilities P with a given X with the subscript I. Entropy is defined as, now here, so we're going to define, we'll use the H as a function of entropy, and it will have the whole set, the probability distribution, like a tensor or a vector, the whole set of values of your data going into the entropy is going to be equal to the following formula. And this is where it gets fun. So if you sum, and so you're going to sum P X. So X of X, the small x, fetches from the big X an element of the big set. And you have a little x or xi. So a specific X pulls out of the big set, capital letter X, and you fetch one little x, and that's your probability, a random number, let's say 0.25. And then you take that random value that you got back, you had some other number, but when you computed it, you got 0.25, and then you got log B. So it's a binary. In this example, it's binary. It could be NAT, could be decimal, but here is log binary. And what follows next is the same thing as before. You take that P X, XI specifically, and it returns, say, a random for that given X. It says, oh, that's 0.25. So you got 0.25 before and you have 0.25 after. But that second one, even though you don't see parentheses, log typically is a function. So the px second time there is going into the logarithmic binary function, and it's computed as a negative number, bloop, right there. And so then you times that negative logarithmic number that got returned by that px, and you times it to the pxi at the start of the string, and that value that's returned is a negative value. And you sum them up, sum. Let's say you got 1,400 of them, or 14,000, or 14 million. You sum them all up, and then see that negative symbol right next to that equal sign? You're going to switch it back to positive. So that will be the measure of your entropy on a positive scale. And so that's what's interesting about math. It's a user-defined function. You can make a function anything you want, and you could say, from 1 to 100 do this, and from 100 to 200 do that. So here we take some probability distributions. One goes inside the logarithm, and then you times it by the other probability distribution, which is the same as the first, the one that went into the logarithm. You times them together, and you sum all the way through the vector, and then you reverse the symbol to make it positive, and that's your entropy. So that also gives you probably a better insight into the way the math works, and gives you, now you have a better idea. So cross entropy quantifies how well a predicted probability distribution Q approximates the true distribution P. Okay, so this is pretty good. So Q is the predicted probability distribution, and P is apparently the true distribution. So as I recall, P is like, as an analogy, P would be your ground truth, and Q is well, I think it's something like similar to your loss function, where it's like your prediction, and we're going to see how well it does by comparing the P and the Q. So you got H entropy, P comma Q as inputs, and here is how it's defined. It's very similar as the last equation, but instead of Px, you have that at the start, and the one that goes into the log is Qx. And so then you multiply them together, sum, and reverse the symbol, making it positive, because it's always on after that summation. All that, you sum it up a billion times, and then it's going to be a negative number because of that logarithm. And then you reverse it, and so entropy, in this sense, cross entropy will be also a positive value. So okay, this measures the distance between P and Q. Okay. Whoop. Well, quote unquote, but we have specific formulas for distance as well. So let's see, we're up to 24. We're also at 10:46, well, Eastern Standard Time. So here we got slide 24, the perplexity metrics. Okay, so now we're going to do perplexity metrics. Maybe we'll get a better intuition of how that works. So perplexity is an exponentiation of the cross entropy. Okay, yeah. So right here you got B, HP, and specifically that is equivalent to the following equation. So you're going to be summing up PQ, and that will be multiplied by the log of PQ going into that logarithm. That's the first type of perplexity, which is more similar to based on entropy. Okay, that's the type of perplexity based on entropy. It's only got one set PX, whereas the perplexity that deals with cross entropy is below, although I just noticed it doesn't show that equation. So it would be nice if I had shown that equation. Anyway, this screenshot is not is from Perplexity AI. So I studied all the four major metrics using Perplexity AI, and it's really great using a tool like Perplexity AI for being your math tutor. It's really great, but you have to be really observant. For example, when I noticed that binary, I noticed that right here, the summing up px log px. I couldn't understand that. I had to ask several questions to learn that second px is going inside of log, and even though there aren't parentheses, and sometimes there are parentheses used, and sometimes there aren't, and that's because mathematicians will understand it to be a function without the parentheses. They will say, "Oh, that's logarithmic function." So when you see log, it's a function, and so even though there are not always parentheses to receive the p parentheses q as a parameter, you can still put them there and say, okay, so pq surrounded by parentheses, and that goes into the logarithmic function, and then it returns 0.25. And so you have that first 0.25 and you got the second 0.25, and you multiply them together. That's so you're learning math. It's just you have to ask very careful questions, and you can't always type the characters, and so you have to say the symbol for summation, blah blah blah, and you got to do it 15 ways, and then finally you get the right intuition, and over time you'll learn. So it's showing you two different ways to calculate perplexity, but I would probably want to study the math a little bit more to get perplexity down, but you get the general idea. It's the side on the left-hand side is showing you the way the symbols are. It's like you're defining a symbol is defined as this function, and on the right-hand side, you have to learn how it's processed. The formula. This is a function, and this is multiplied by that, and therefore blah. It's very challenging, but using AI as a math tutor is fantastic. Okay, next one is slide 25, perplexity, interpretation, and use cases. So as discussed, cross-entropy perplexity, BPC, bytes per character, and bytes per bit, bits per byte, rather, are variations of language models, predictive accuracy. And in this book, Chip Huyen will use perplexity as the default language modeling metric. She also says that the more entropy the model has in predicting what comes next in a given data set, the higher the perplexity. Okay, I mean the more uncertainty in the model. So the more uncertainty in a model in predicting what comes next in the data set, the higher the perplexity. And so naturally, you just have to study these math formulas more and more and more. And also, how does it look in the computer code? Because sometimes it will look a little bit different. Usually it's easier to look at the computer code because oftentimes it's like a black box, and that whole ugly math formula is just a simple formula, and you just put the value in it. So sometimes it's easier looking at like the Python code that actually does it. Okay, so now slide 26, perplexity, interpretation. Oh, in use case, continued. I see we were here, and now we're continuing. So what's considered a good value for perplexity depends on the data itself. And so I need to correct that. And how exactly perplexity is computed, such as how many previous tokens a model has access to. Oh, I see. Yeah. Here are some general rules. So more structured data, not just text data, but say, like JSON data, etc. Something with a little bit more structure, then a lower expected complexity. If you have a larger vocabulary, then you can expect greater complexity, but a longer context length means lower complexity. So those are some good intuitions, and that pretty much makes sense. So again, wow, third, perplexity interpretation and use cases. So for reference, it is not uncommon to use perplexity values as low as 3 or even lower if all tokens in a hypothetical language have equal chance of happening. That's just a simple hypothesis or assumption to provide an insight here, because that's not always going to be true. But if all tokens in a hypothetical language have equal chance of happening, a perplexity of 3 would mean that the language has 1 in 3 chance of predicting the next token correctly. So that's kind of a good insight there. If a model's bad at predicting the next token, its performance on downstream tasks will be bad, obviously. And OpenAI GPT-2 report shows that larger models consistently give lower perplexity. And so that's why, for a long time they wanted larger and larger models too. But now there's also a big trend in making smaller models that are quite powerful as well. And some of these small models are really amazing. So next, we're up to 28 hour, almost to the end of the hour. So naturally, you can interrupt me at any time. Also, I think the first 60%, 65, 70% of the chapter, it's got a lot of great material, and then it sort of meanders towards the end. So I think if you want to master chapter 3, you want to definitely be more focused, I think, on the first half. On the second half of the chapter, it's more certain interesting ideas that are more generally presented, but also a little bit more disconnected. I think you want to focus more on the first half of the chapter, and enjoy the math of it, because that's where you're going to get a lot of good intuitions. So chapter 20, slide 28, perplexity might not be a great proxy to evaluate models that have been post-trained using techniques like SFT, which is the
supervised fine-tuning.
supervised fine-tuning, and the RLHF, which reinforcement learning, and I forget what HF is.
Human feedback.
Yeah. So in other words, perplexity may not be as well suited for the fine-tuning. It's better with just evaluate that have been post-trained. So just with the pre-training, so it may be better sometimes for just the pre-training stage. Post-training is about teaching the model how to complete tasks that are more aligned to humans, and so it's not going to always be as good at predicting the exact next token, because it's now a little bit more politically minded to be aligned with the way humans think. So if you in other words, perplexity might be better for the pre-training rather than the post-training. And specifically when you're evaluating a model, it might be more at that pre-training stage. Otherwise, I'm sure there's different ways to measure the post-training. So onward, a language model's perplexity typically increases after post-training. Collapse after the post-training collapses the entropy. So, in other words, when it becomes more aligned to the way humans think, then there'll be a little bit more entropy because it won't be as simple at predicting the exact next token because it's aligned a little bit more to think like, to be more suited to human thinking. All right, so that was pretty cool. And slide 29. When evaluating a model's performance, it's important to differentiate between exact and subjective evaluation. And so the next several several slides are quite interesting and talking about exact versus a subjective evaluation and all the different ways it can be done. And it's actually, these are really important. And if you scan through all of them, it's really interesting. So exact evaluation produces judgment without ambiguity. For example, if the answer to a multi-choice question is A and you pick B, you're wrong. There's no ambiguity about that. 2 evaluation examples that produce exact scores. Functional correctness and similarity measurements against reference data. So this looks all easy, and then later we'll be talking about it again, if we get that far. And in any case, you have to really master all these things because you'll be using it over and over again. So we're talking about exact evaluation versus subjective evaluation. And then there's 2 ways for exact evaluation to be exact. It could be functional correctness or similarity measurements against reference data. And so that's just for being exactly correct. And then we'll be talking different ideas in terms of subjective evaluation. And so it's very interesting. And you have to master all these different ideas because this is the way you're going to evaluate your model. And there will be trade-offs at every step. So now, exact evaluation, functional correctness. Go ahead. So functional correctness. And here we say functional correctness. Functional correctness evaluation means evaluating a system based on whether it performs the intended functionality. And the example makes it very clear. For example, if you ask a model to create a website, does the generated website meet your requirements? You ask a model to make a reservation at a restaurant, does the model succeed? Functional correctness is the ultimate metrics for evaluating the performance of any application, as it measures whether your application does what is intended. So that's what functional correctness is. And you can do it with a prompt, and there will be very great, great slides on how that unfolds. And yet, we're kind of still theoretical. Maybe the next chapter will be more hands-on. I'm not sure, but this is still very general. But you'll be doing it all the time, and the details. The devil is in the details. You have to master these. So right now we're just talking about functional correctness, and we're already going to drill down to understand it completely. And then we'll do the one with reference data. So functional correctness isn't always straightforward to measure, and its measurement can't be easily automated. But sometimes it can be automated, which we'll see in a moment. Code generation is an example of a task, a typo, of a task with a K there, where functional correctness measurement can be automated. So in the case of code generation, you can use functional correctness, but other times it's a little bit harder to do functional correctness. Popular benchmarks for evaluating AI code generation capacities, such as OpenAI's Human Eval or Google's MBPP, use functional correctness as their metrics. So it can actually be done sometimes and quite effectively. Exact evaluation. Similarity measurements against reference data is the other way. And if the task you care about can't be automatically evaluated using functional correctness, one common approach is to evaluate AI's output against reference data. If you ask a model to translate a sentence from French to English, you can evaluate the generated English translation against the correct English translation. Each example is a reference data. Each example in the reference data follows the format input, comma, reference responses. And for example, again, we're on similarity measurements against reference data. An input can have multiple reference responses, such as multiple English translations of an English sentence. So you could have 3 responses to cover the input, and compare which one is the closest or which 2 is the best. So, actually, they're included, so they're the way you would want them translated. They're all good, and it has to be closer to one of those ground truths, Reference responses are also called ground truths. Since this evaluation approach requires reference data, it's bottlenecked by how much and how fast reference data can be generated. Reference data is typically generated by humans and increasingly by AIs. Next slide. Similarity measurements, again, against reference data continued. Human-generated data can be expensive and time-consuming to generate. AI-generated data might still need human reviews, but the labor needed to review it is much less. And there are 4 ways to generate the similarity between 2 open-ended texts. So it's like anything, you're going to forget this stuff, but you can scan through it and say, oh, this would meet what I am doing, and it's well suited for this or that. And it's like anything, you got to go through 24 slides or whatnot, or notes, and you go, this is the one, and you study it and 3 other books, and you realize this is the way I'm going to solve the problem. Okay, so now we're still talking about similarity measurements against referenced data, and you can ask the evaluator to make a judgment between 2 texts that are the same. You'll either have an exact match, or you could have a lexical similarity or a semantic similarity. Lexical similarity is like they look similar, like you count the number of tokens between this statement and that statement, and they're almost the same because they share more tokens. Semantic similarity, on the other hand, is more about the meaning, because you could have 2 idiomatic statements and they're the same. Like it's easier to skin a cat, and you say the same thing in a different idiomatic way, and they share no tokens, but semantically, the 2 idioms are exactly the same, more or less. Therefore, they are semantically similar. So semantics is about meaning, and lexical is like the form is similar. And so you use those type of words in logic as you get into very advanced logic. So these kind of things you will see in logic and even in math. It's important. 2 responses can be compared by human evaluators or AI evaluators, and AI evaluators are increasingly common. And so lexical similarity. So we already talked about that. And semantic similarity, we talked about that. You can review these slides accordingly. So again, semantic similarity is more, but we've pretty much already discussed it. And it's like anything, you're just going to have to do more studies. I got a lot of slides here. So semantic similarity is like sometimes called embedding similarity. And so it's like the very fundamental concept of gradient descent, where you got 2 objects it could be a multimodal model, and you're trying to see whether the concept of cat is similar to something like a picture of a cat. So, is this a cat? And you got a picture of a cat, and semantically, the similarity would be very close, because when you do like the Pythagoras theorem, which specifically if we do the Euclidean distance, which is a direct application of the Pythagoras theorem, it's just saying point A minus point B squared plus blah, 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 blah. It's very easy. On this, you can get a lot of good help studying it on AI, using Math Tutor. AI as a math tutor, you can easily learn this concept very well. And that's the whole concept of how gradient descent is kind of calculated, as an example. So, introduction to embedding. So it talks about how embedding works, and you really the book by Sebastian Rask, Large Language Models, Build a Large Language Model, is got some great material on understanding tokenization and making embeddings, and it's definitely a must read. So again, moving further into embeddings, it discusses it more, and we're well over time, so I'm just moving quicker, and I don't need to finish every slide here, but there's a lot here to study and learn. And if you read the book and review the slides, I'm sure you can get a lot of intuitions, and then you use like Perplexity AI to ask more questions, and not just Doubt Group, but several others that are great. It's whichever one you like. I like Perplexity AI because it's sort of like AI with search integrated, so that it's very good at finding what you're looking for. It's really fantastic. And I love it for researching stock market data. It's very good at open-ended questions. So AI as a judge. So this is really an important area. And so the next like 20 slides is all about AI as a judge. But rather than take you through all that, suffice to say that you have to study all of this, and you will get, as you go into AI as a judge, it will go back to previous concepts of lexical and semantic kind of similarity, and so depending on how you're evaluating things, you'll have to use one tool or the other, that kind of thing. And so if the devil's in the details, and you're going to have to know by going through and looking at all the caveats, what's going to work given my scenario here. And this is how, as a creative programmer, you have to pick the right tools to, the right math formula, etc., and to know this is the way to do it. As you find out, okay, because of this caveat and that, I need to use this kind of tool, and as you read the slides, you'll say, okay, this is probably better or that, and so it's like anything too. You can maintain the slides and make them better. So AI as a judge, the challenges of evaluating open-ended responses have led many teams to fall back to human evaluation. However, also, there's many ways that things can be automated, and so Chip Huyen will show conclusively why. At first you think, no, it's not possible, but then you realize oftentimes it's a great way to do things. And we're already out of data, and you need different ways to generate answers, and sometimes it's too expensive to do it with humans. So you got to use AI as a judge, and that doesn't always work. And so there will be caveats for and against, and for certain tasks, it's a great way to do things. So again, AI as a judge. There's a whole bunch, another 20 slides. You can ask AI models to judge an output based on a criteria: correctness, repetitive, toxicity, controversial, bad language, whatever, wholesomeness, hallucination. So oftentimes, for example, you can use AI to help trap or prevent hallucinations. There are ways to do that, and many ideas will be suggested. With the right prompt for the right model, you can reasonably get good judgments on a wide range of topics. Agreement between GPT-4 and humans reached 85%, which is even higher. So in other words, agreement between GPT-4 as a judge, I think, and humans. In other words, the judge was the GPT-4, and humans also asserted or believed in the same thing, and there was 85% overlap, which is higher than agreement among two humans on this, evaluating question after question. It only scored 81% in a recent study. So that's interesting. In other words, you can't necessarily say AI as a judge doesn't work, especially when you get results like that. So sometimes it can work. Not only can AI evaluate a response, but it can also explain its decision, which can be especially useful when you want to audit your evaluation results. So not only will it say number 4 or number 5 is the best, given your prompt, your input prompt, and the question and the way it was qualified, but it will also provide an evaluation. It'll say, this is why it's the best. And so as someone trying to improve the model, you can look at that response. So sometimes humans, of course, are still involved. And so you've got an AI judging things, and then a human will look at the explanation of why AI chose option 5. And this helps you to say, okay, I agree. And so this is the way things can be automated and improved. Its flexibility makes AI as a judge useful for a wide range of applications. And for some AI applications, it's the only automatic evaluation option available. Okay. Like I said, you can interrupt me anytime. I'm just sharing, but also this is still quite good. And then maybe the last 20 slides are more general. How to use AI as a judge again. Well, yeah, we're still in it. We're in AI as a judge, but how to use AI as a judge. There are many ways you can use AI to make judgments. For example, you can use AI to evaluate the quality of a response by itself, compare that response to reference data, or compare that response to another response. In other words, the devil's in the details. And like I said, you would have to look at 20 different slides, 3 books, and this and that, and this qualification, that. And say, oh, this says this is better for reinforcement learning. This is better for pre-training. This is better for post-training. And as you address all these qualifications and finally pick the best little rat trap, then you got to implement it correctly. And then that's dicey too. You're going to have to make the exact prompt and make sure that prompt is well qualified and you're getting the kind of responses you want. And it's trial and error until you got, okay, now it's working. Now, this is the fun of being an engineer or programmer and iterating over a problem. So there are many ways you can use AI to make judgments. So we say, okay, for example, we did that. And then here are some naive example prompts, and they're quite good for these 3 approaches. So the 3 approaches are in the second bullet. Whether you compare it by itself, compare that response to reference data, or compare that response to another response. So here, AI as a judge, we evaluate the quality of a response by itself, given the original question. For example, given the following question and answer, evaluate how good the answer is for the question. Use the score from 1 to 5. 1 means very bad, and 5 means very good. Question, and then you would insert the question there, answer, the answer, and the score is available so that the model, that's the prompt for the model. If you've never studied prompts, this is an area that is fundamental. Oftentimes you can hack a solution so well or play tic-tac-toe between two LLMs playing tic-tac-toe or chess. One could be an API online, the other could be local. And so they both have similar prompts. One is the player, one is the host, back and forth, back and forth. You can find these fun things on the internet, and they're really great to play with, and you'll get much better intuitions of how to make things work. So you have to understand prompt engineering. If you understand a little bit of how to do prompting, then this is a template, and it's going to be filled with the question, the answer, and the AI will say, oh, my score would go there. And so it knows that a bad answer is going to be weighted as 1, a good up to 5, and in between accordingly. So it knows I got a scale of 1 to 5, and I got a question, I got an answer, and I'm going to provide the score, because the directions at the start, given the following question and answer, evaluate how good the answer is for the question. Use the score from 1 to 5. Great. And this is an example of doing a question by itself. Next, where it's 2 questions. And so you can see already you got a reference answer, a generated answer. So you got a question and a reference question, and you're going to be comparing them. Given the following question and reference answer and the generated answer, evaluate whether this generated answer is the same as the reference answer. And so the output will be true or false. So the question is question, and you're going to compare it to the reference question, and are they the same? And the generated answer is going to be true or false, apparently. So as another good prompt. And finally, the third example, as I recall, there were 3. And so we're going to compare 2 generated responses and determine which one is better, or predict which one users likely prefer. So given the following question and 2 answers, evaluate which answer is better, output A or B. In other words, it has to pick A or B. So you got a question, you got the first answer and the second answer. And so the LLM, or the foundational model, is, or whatever model you're using, is charged with picking which answer is better. So you're just following. There was 3 ways you could evaluate reference data by itself, or like comparing Baba or this or whatever. That, once again, you forget these things too 5 minutes later. If you just, the devil's in the details on your, I'm making them something like this, and I need this kind of question or that or this or that. Oh, this one is perfect. And then you're gonna edit the model, the question, the prompt a little bit to fit your precise requirements. Tic-tac-toe or whatever. So right now we're in a long run. We're doing AI as a judge, and it's got great details. How to prompt an AI judge. How to prompt an AI judge. Similar, obviously a typo there, is similar to how to prompt any AI application. Okay, so it's similar. And exactly. In general, a judge's prompt should be clear and explain the following. This was a good insight. The task the model is to perform, the criteria that the model should follow, and the scoring system. So this is a higher level, a more general intuition of how to design the prompt. So we could get into the last 2, but bullet points, but you get the idea. And it's very easy to follow this. So here, furthermore, prompts with examples have been shown to perform better. So this is helping you make the prompts better for whatever you need to do. If you have a scoring system between 1 to 5, you can include examples of what a response with a score of 1 or 2 or 3 or 4 or 5, how each one would look. And by just providing an example for each one, you're helping the AI model know how to use them better, and you might get better results. Okay, sometimes it may help. I think if you got the intermittent problems or somehow it doesn't seem to perform, you have got to edit it. And this is how, these intuitions will help you make a better prompt. An AI judge is not just a model, it's a system that includes both a model and a prompt. Altering the model, the prompt, or the model's sampling parameters will result in a different judge. Okay, and limitations of AI as a judge. Despite many advantages of AI as a judge, many teams are hesitant to adopt this approach. Here are some concerns. The probabilistic nature of AI makes it seem too unreliable to act as an evaluator. And AI judges can potentially introduce non-trivial costs and latency to an application. Given these limitations, some teams see AI as a judge as a fallback option. However, the next few slides provide even more insight, and sometimes this can be overcome. Inconsistency. For an evaluation method to be trustworthy, its results should be consistent. Yet AI judges, like all AI applications, are probabilistic. So this is a problem because you could add the AI judge could be asked to return an answer more than once, and sometimes the answer will vary. For example, Xing et al. Showed that including evaluation examples in the prompt can increase the consistency of GTP4 from 65% to 77.5%. So by having examples of how the evaluation 1 through 5, for example, had to specifically be used, by giving guidance of what one would be an example of something that's only 1, an example of something that's great and is 5, by showing examples of each one and the evaluation examples, defining them. This helps GTP4 dramatically by 10%, all the way up to 77.5%. It improved its performance that much. However, they acknowledge that high consistency may not imply high accuracy. It may always return the wrong answer consistently. So it doesn't always work. And it's like anything, as you're designing a system, you have to see, is it working properly? And if it's not, maybe there's something wrong with your prompt, for example. Or maybe you have the wrong tool and it's not good for this type of model or that kind of model. Like, some ways of doing things will be good for reinforcement learning. Some other things are good for post-training, pre-training, this training, that training. Likewise. All right. Criteria ambiguity. This was okay. This was interesting. It just mentioned that different systems like MLflow, Ragus, and Llama Index have a criteria known as faithfulness, and yet there's no. It's not comparable, but between the three systems, for example. And
Mhm.
so things can be ambiguous and relative between systems, and you can't always say, oh, they're the same, they're related. All right. I hope you found this useful. Do you want me to continue, or how are you doing with the time?
We have 2 minutes left,
Oh,
so
okay.
I don't know
Okay.
if you have something else that you would like to share, anything uh, important, or you feel that everything has been covered, I think.
Yeah, I mean, if you go through,
Mm-hmm.
since we're not out of time yet, if you go through just we only have about, well, yeah, 5 or 6 more slides. So increased cost and latency, biases of AI judges. This is all easy reading and yet sometimes quite insightful. And this is certainly a possible way that for some problems, not for all problems, and it's the devil's in the details, but as you put things together, you might realize that this is a perfect fit for AI as a judge. Chip talks about, for example, can a weaker model judge a stronger model? Apparently, yes, because generating, say, generative text, when you generate a creative writing piece, when something is done like that, you need a stronger model. But evaluating it, you don't necessarily have to have quite that same level of strength, and evaluation can sometimes be faster with a smaller, streamlined, high performance model.
Mm-hmm.
As bigger models are sometimes a little bit slower for some tasks. And so it goes over, can a weaker model judge a stronger one? Can two models of the same strength judge each other, etc.? Sometimes you can divide, and one is the judge and the other is providing the content generation. So there's different ways you can design your system, and there's lots of good ideas, you know, provided. Like, for example, using a model to judge itself as a sanity check, or to help stop, hallucinations. So 59, almost at the end. So one exciting area of research, which I just alluded to, is specialized judges. And specialized judges are trained to make specific judgments using specific criteria, uh, and a specific scoring system. And we saw that we do that stuff making the prompt. A small specialized judge can be more reliable than a larger general purpose judge for specific judgments. And there are many possible ways to use AI judges. And here are 3 examples: reward models, reference based judges, and preference models. So that's what we go on: 3 prompts: reward model, reference based judges, and then preference. But it looks like I deleted that slide accidentally. So I need one more slide. But anyway, this is a good first draft. I think it's a pretty good, it's got a lot of good content there. It could easily
Mm-hmm.
be improved by anybody willing to share the URL. Send it to anybody that needs help.
Yeah, if you want, you can send it through the in Discord in the
Okay.
chat. It would be great. I think it was a very, very good summary. All the key points in the chapter are there. And yeah, I just want to say like thanks for taking the time to make this and to present it to us. It was great. I don't know if anybody has any questions.
Okay. So I'm gonna. I said stop sharing.
Yeah.
Let me see if I
Yes.
can give. Oh, there you are. There you
Yeah.
are. Yeah. Any
Nice.
questions?
Yeah. I saw lots of comments in the chat. Michael, I saw that you have applied many of these techniques. I don't know if you have any extra comment that you would like to share.
Yeah. I've used AI Judge very successfully in some applications at work, and We've actually built a pretty good system where we have sort of like a data flywheel where we do humans like we'll do lots of evals, and then we can feed those back into our AI as a judge prompt. So we can, give sometimes even like hundreds of examples, like case shot examples. So the prompts get pretty big. But what's great about that is we can use some of that data for improving our prompt, but we can also keep some of it out to like evaluate it against human judgment. So we can eval our AI judge and see how well it correlates to human judgment. And for one application work, for instance, we really cared about precision. So our AI judge is just a sort of a binary classifier, and we found, for instance, like we could get it up to like 98% precision with a really good prompt, and lots of prompt engineering and kind of like going through, cases where the AI judge gets things wrong, and then you go back and you sort of improve your prompt over time, and that works really well. And then even beyond that, you can then, if you have a pretty good data set, then you can look at like fine tuning. So you could fine tune an AI judge as well, so that you don't need this massive prompt, for instance.
Nice.
So, what kind of a model that you used? Could you describe like or give empirical examples of the models like you used, like GPT-4o or Gemini, for example?
Yeah, we use Gemini, and we had it's interesting because we have Gemini, like not a strong model, but a cheaper model, like their they're like kind
Flash
of like
Mini? Yeah.
flash, yeah, model to generate content, and then we have a stronger AI judge that runs the AI judge prompt. Um, and for our case, like I said, like precision is really important. So we care about, it's okay if if our model generates some content that we discard and we don't present to end users, because we're pre-generating this content. But we really care about it not letting like hallucinations slip through. So it's okay for us to have a stricter AI judge that it might discard some good content, but we can make sure that like most of the content it deems as accurate actually is accurate.
Nice. Any last questions before I ask who would like to be the next chapter lead? Any additional comment? Nope. Then is the time in the poll. So next week we're gonna start chapter 4, and I was wondering if anybody would like to take the lead on this chapter. Do a great job as Patrick or as Carlos last week, where they explained to us and summarized this chapter and with the discussion.
I can take chapter 4. I want first
Nice.
to congratulate Patrick for his amazing, inspiring, and motivational presentation. Really, I'm not kidding. I mean, I'm impressed, and
Thank you.
what you did today in this
I'm not.
it's
I'm not an
motivational.
expert.
It's motivational. Yes,
Yeah.
it doesn't matter. It doesn't matter. You are. It was a motivational session for me. Thank you very much, sir.
You're welcome. Yeah, I mean, like I said, I'm not an expert of everything, but I'm self-taught in logic, and even I started studying probability theory, this, that, the other, and I'm not an expert at everything. And so, if I misspoke about a couple things, well, I'm not going to say everything is perfect, but I think I'm excited about it. So I think if I keep on studying, I will be getting into it. So I'm enjoying it too.
You did an amazing job, sir.
Thank you.
Yes, pretty good. And thanks for taking your time, because I'm pretty sure
I love this
that
group too,
took a
because
lot of time.
it motivates me. This group, it makes me, because I probably wouldn't read the book as closely without this group. So it's really been a useful way of studying the book, because otherwise I would just speed read it and I wouldn't get half of what I'm getting out of it.
Nice. I'm glad to hear that. And I had one question.
Word, you're on mute.
Yeah, yes, Patrick. Yes, thank you. Thank you much. So you should be aware, sir, that it's not that you motivate yourself, but you should be aware that you are motivating a lot of other people. It's a big deal. I mean, it's something I never seen in my life, but I experimented today. I wanted to share it very openly and transparently. I'm super impressed. I never seen that in my life. Thank you very much, sir.
Thank you. Yeah.
Awesome. Nice. And Patrick, I had one question regarding the learning math part. I wanted to ask if you're using, for example, any roadmap or are you following anything in particular, or you are following like your interests? Because I saw one tool that I've been seeing in a lot of places and I'm like eager to start, that is called Math Academy, which looks great, but I don't know what's your take on that.
Well, I have several books on math theory of machine learning and AI, and I have one book. The guy was Mass Institute of what is it in Massachusetts?
The MIT,
Huh?
the MIT, you mean? Or
What's that great technical college in Massachusetts? So I got these books for professors that wrote for some, they're from the best universities, and it's just it's so thick and beyond me. But I just in this example, I just focused on the math equations presented by Chip Huyen, and then I went to the internet. I used Perplexity AI, and I was able to get more and more out of it just by studying it over and over and over again. Not perfectly. I still have to study a little bit more on the Perplexity and exactly when you can use it and which metric is better for this or that. But a lot of these things are easier actually in the computer code. So I have a bunch of math books. I can't say I'm a master of all of it, though. It gets so advanced.
cool. Anything else before we say goodbye? Nope. Then again, thanks, Patrick. That was a great presentation, and then thanks, Ed, for taking the lead next week. See you Sunday.
Great job.
Great.
Thank you.
Look forward to it.
Bye.
Thank you. Bye. Take care.
Bye.